Excellent. But today's topic, I will talk about some electrospoon fibrous scaffolds that we are preparing. We are working on in our lab, and their potential use is as wound dressings. The electrospoon fibers are like that, like the background of my slide, like you can see. Uh, this is these fibers creates a three-dimensional structure that it can be interesting with many interesting applications and properties. So as you said, I'm from Mexico. I live in Tijuana. It's in the line border of in United States, close to San Diego. So this is my university. This is surrounded from mountains. The content of this talk includes some introduction of the wound dressings, the electrospinning process. I will explain a little bit, and some results that we have about one of the projects that we are working on, and some summary. The electrospinning technique is a process, is a method that creates nanofibers, electrospoon, nano or microfibers, in order to have a three-dimensional structure that possess different properties depending of the loaded bioactive compounds. You can load into the fibers or at the surface. You can load vitamins, proteins, plasmids, so several drugs, and you can make it with a core, or you can load the components at the surface. So this electrospoon technique, electrospinning technique, possess a shrink pump where you can control the velocity of the injection of the polymeric solution. Also includes a high voltage supply. Usually we use 20 kilovolts, but it can be used with 5 kilovolts to 30 kilovolts. And this high voltage supply creates electrical fields that attract the polymeric solution drop to the collector, a metallic collector, which is conductive. So when you apply the voltage, the electrical field is created, attracts the polymeric solution to the collector, and then it's elongated and creates a fibers in the air, and the solvent is evaporated with this process. So the fibers are collected randomly to the metallic collector, as you can see at the image, or you can do some patterns. Why these nanofibers are interesting for us for wound dressings? Because we can prepare fibers between 100 to 1,000 nanometers, depending of the conditions that you use in the electrospinning process. There are several articles that have been published that reports sizes less than 10 nanometers. You can control the high surface area. You can control the surface area. It's important for us that is high because increase the contact sites in a minor spatial radius. We can control also the pore size of the final wound dressings. This wound dressing can have low density, can be made using biocompatible polymers, biodegradables. We can control the degradability. These final materials are flexible, elastic, with desired mechanical properties, depending also of the application, and can be bioactives. Depending on the bioactive molecule that you use, you can use antimicrobial, anti-cancer, anti-inflammatory molecules. So I present to you some GIF that represent the electrical field, how it's working, how the electrical field is attracting the polymer solution to the collector. So the electrical field elongates the drop and creates the field, as you can see on the image. You can have two types of collectors. You can have an static collector or a dynamic one. If you have a dynamic collector, you can create patterns. This will increase mechanical properties and is useful for certain applications. And uh, you can have a static collector, and you will collect randomly the fibers. This is important in biomedical applications such as tissue engineering, because we want to simulate extracellular matrix in order to or improve the wound healing. If you see or if you check literature, you will find that electrospinning technique is easy and versatile, but uh, we, we need to take care of different conditions, different parameters in order to create successful fibers. And also we can modify these parameters to control diameter and pore size of the final wound dressings. Uh, the molecular weight of the polymer is important, the polymer concentration of the final solution, the conductivity of the solvents that you use, the surface tension. Also, the applied voltage is important. All these conditions are important, and temperature and humidity affects the successful production of fibers. Sometimes this humidity give us a headaches to the lab members because affects the fibers production. And today's topic is about wound dressings. We look for several applications of these electrospoon fibers in the lab, but today's topic is wound dressings. There are many wound dressings in the market, many options, but some of them has many drawbacks. Between them is that they attach to the injury, and when it's removed, uh, destroys certain tissue. Also, it's easy to contaminate with the ambient bacteria. So we want to propose a wound dressing that does not attach to the surface and avoid microbial contamination. So we will add some antibacterial components to these wound dressings. And we have been publishing a lot of work using nanofibers to perform or to create or to propose effective wound dressings. We have been, this lab had certain experience in that. And we used to create multi-layer systems to create these wound dressings, adding a degrading level where the fibers is loaded with a bioactive component, and when the fiber degrades, the component is released to the injury. So this bioactive compound can have antimicrobial components or growth factors, or can have different useful components. So it is well known that fibers accelerate the wound healing. So creating this three-dimensional scaffold that is helpful for cells to migrate and proliferate inside the fibers. We have been working in a system that has or possess two polymers, polycaprolactone and polyvinyl pyrrolidone. Polycaprolactone gives the mechanical properties to the final wound dressings. Is hydrophobic, degrades in longer times, like 6 months, for example, and has good mechanical properties. And the PVP, which is a hydrogel, degrades easily in contact with humidity, and usually is loaded with the bioactive component. So this layer degrades and release the the component, and the PCL is useful to protect the whole wound dressing, the whole injury. So in certain publication, we have been loaded silver nanoparticles. We have been loaded several drugs as propanolol, sildenafil citrate, dexamethasone, and others. In today's topic, load these fibers with a Shack nanocomposite that is made of chitosan, silver nanocrystals, and graphene oxide. All of them has many properties that are interesting to the biomedical applications. Chitosan and silver nanocrystal has antimicrobial properties, and graphene oxide has uh, promote conductivity and promote mechanical properties. So in a previous work, already published in scientific reports from Nature, we published the synthesis of these Shack nanocomposites, and right now we are working in the corrections of this article, this topic, where we load this Shack nanocomposite into the PCL PVP fibers. So this is how it looks, the electrospoon fibers, the final wound dressings. As you can see, the surface is smooth and it's a multi-layer one, so you can control the shape of the final wound dressing. You can see the fibers, how they are being created on the tip of the shrimp. You can see it. And the specific objective of this study that we are working on right now is to synthesize a multi-layer fibrous system made from Shack nanocomposites and PCL PVP fibers using the electrospinning technique. We perform several physicochemical characterization using FTIR, TGA, DSC, which are thermal analysis. We also perform microscopy and X-ray tomography. And also we evaluate the mechanical and biological properties of these final wound dressings. In our previous work, we synthesized the Shack nanocomposites. Our colleagues use garlic as a source of for reduce the silver nitrate, and they create a silver nanocrystal with sizes of 2 to 10 nanometers. After that, they added some oxidized graphene to the reactions, and after that, they added chitosan in a 2% of weight over volume of the final reaction solution. Then they filtered the solution with a nitrocellulose membrane using a 0.2 micrometers of resolution. And that one, I put it onto the polymeric solution. I immerse this nanocomposite into the polymer solution. I present to you here the condition of the reaction to prepare the polymeric solution, when we use two solvents in order to dissolve the two polymers that we use. The PCL was the major component of the polymeric solution, and the PVP was the minor component, because we want that the final result possess good mechanical properties, and just certain percentage of the fibers degrades and release the Shack nanocomposite. So at the end, we want to create fibers that has encrusted these Shack nanoparticles onto the surface or inside the fibers. So we can release slowly the composite into the injury. Here we use these conditions to create these nanofibers. Before that, we attempt to create different systems using different conditions. And this one here are the optimal ones, with the best results. And we add 3 different proportions of the Chuck nanocomposites onto the polymer solutions using 1, 5, and 10% of the composite. I'm sorry. In general, in the case of FTIR, we saw or we confirmed the presence of the PCL and PVP polymers, and we found characteristic signals of the chirosans present here in this part of the spectrum. So, but this analysis was not enough to evidence the presence of the Chuck nanocomposites into the fibers, because most of the components are made from carbon, hydrogen, nitrogen that has the same elements of the polymers. So we use thermal analysis to help us to evidence the presence of the Chuck components. And happily, we found that when we increase the temperature until 800 degrees, the fibers with higher concentration of the Chuck nanocomposite does not degrade completely. As you can see here, we have residual components of the Chuck component of 5 and 10%. And we almost, in the PCL and PVP control, the pristine polymeric control degrades completely. And here we evidence the presence of the silver nanocrystal and graphene that are resistant to high temperatures. So this is one of the evidence. Also, we performed the STEM analysis using EDX filter. And here we obtain fibers between 1 micrometers to 2 micrometers. Also, we have fibers of 600 nanometers. And but these diameters are okay because we are looking for a wound dressings. So we need thicker fibers in order to improve the mechanical properties. So in tissue engineering, you want to create thinner fibers using like 300 nanometers, but for this application of wound dressings, these diameters are okay. And as you can see, applying the EDX filter, we obtain signals for silver. So in the pristine PCL PVP control, we don't found any silver signals, as you can see here. But in the 3 samples, when we added the Chuck nanocomposites, we obtained the presence of silver. As you can see, the proportion of the content of silver is proportional to the content added of the Chuck nanocomposite. So this is a good evidence of the successful addition of the Chuck nanocomposites onto the fibers. We also perform an X-ray tomography in order to see or observe the 3-dimensional structure of the fibers. As you can see in this tomography, there are 2 colors. The white one or gray one represents the fibers, and the red one represents the air contained in the final wound dressing, representing the 24% of the total volume of this final object. And this air percentage is important because allows the oxygenation of the injured area and promote the re-epithelialization and proliferation of cells inside these fibers. So this is a good resource. We can also observe the interconnection of the pores between fibers. In the right side of the image, we can see the interconnectivity between the pores. So this is a successful 3-dimensional structure. In the case of mechanical properties, test different properties. We calculate different parameters such as the stress, the final stress, the elastic modulus, the elongation arc break, and the tensile strength. And comparing the three samples and the pristine control, we found that the 5% Shack nanocomposite fibers are the ones that are more interesting in talking about the elastic modulus, the stress, and the tensile strength. So only the elongation arc break was better than 1% Shack nanofibers, but most of them, the 5% was the best. We use a load of 15 newtons to perform the analysis, and usually the velocity is the standard that we use in this norm of mechanical testing. In the case of the biological evaluation of the fibers, we perform the antibacterial analysis using two examples of of bacteria, gram-positive and gram-negative bacteria using Staphylococcus aureus and E. coli in order to compare the effect in both kind of families of bacteria. And as you can see, the E. coli was more sensible to the Shack nanocomposites. When we incubate the bacteria in presence of the materials for 24, 48, and 72 hours. At the end, after 72 hours, we obtain the best results when the Shack nanocomposite decrease importantly the proliferation of the bacteria. In the case of E. coli, in the case of Staphylococcus aureus, the replication of the cells was reduced, but it was not that important or interesting. At the contrary of the E. coli, that kills almost 50% of the population. So this is due to the difference between the cell wall, where the cell walls of the Staphylococcus aureus is thicker and prevents or protects the cells from the attack of nanoparticles or nanostructures. In the case of biocompatibility, using fibroblast L929, which is from mouse, we test the different fibers and the pristine control to these cells. We incubate the samples for 24 hours in presence of the cells, and after that we perform the MTT assay. So we can see in the results that the composite with higher concentration, 10%, has the less cell viability, but is around the 80% of survival. So the norm ISO 10993 give us tolerance until 70% of reduction of the cell viability. So all of the samples are biocompatible, but again, the 5% Shack nanocomposite sample was the one with the best results. It is well reported and tested in our previous work that PCL and PVP electrospoon fibers are biocompatibles and promote cell proliferation in cells. And so this is a good resource for us. So in summary, at this stage of the study, we synthesized successfully the Shack PCL PVP fibers, and we want to propose it as a wound dressing, as an effective antimicrobial wound dressings. We performed several characterization on the Shack nanocomposite, which is not shown in this presentation, but it was performed and is in the article that we are trying to publish. And in this slide, I present the physicochemical characterization of the fibers and the biological ones and tomography. So for the mechanical properties, as you saw in the results, the sample with 5% of the composite show the better results in mechanical properties. And also in the antibacterial studies, also that the 5% was the best sample that reduced E. coli proliferation. But between comparing the two bacteria, the E. coli was the most sensible to our nanocomposites, and the Staphylococcus aureus still is resistant, but also decrease a little bit its proliferation. At least don't promote more replication of this bacteria. For future work, we want to perform more analysis on cell culture using different cell lines, using blood lines on human fibroblasts. And also we want to use murine animal models in order to test the wound dressings in vivo. And we want to quantify some immunological molecular markers. And that's the future of the study. Right now, we're trying to publish the result that I present today. And thank you. I don't know if you have any question.